It says 2013 new design, so that the newest design was released in 2013. There's not one since.
I don't think there's one since. This is the latest manual. I saw another manual come out in 19, but I didn't see much difference in the components that they added to the ice maker itself. Um, and I know I have the old manual somewhere, and I was trying to find it so I could. In this presentation, I was going to put the two images side by side so you could compare what was new and what was different. But I'll try to point them out because the cycle and operation of the old one, even though mechanically it's the same, electrically they've made some changes on what causes the ice maker to cycle and drop the ice and some other things. So everything was taken out of that service manual that I sent in the email. So anything that I have appeared here on the screen will be in that manual, so you can go back to it and read it. So I'm not going to read everything to you guys. I'm going to go over uh, the theory, the cycle, the operation, and then some of the schematics and some of the things to look for when testing and troubleshooting. Um, First thing to start off is, okay, so they have these new 15 and 18-inch undercounter ice makers, and they're made, Whirlpool bought so many different brands now. They have a Gen Air version, KitchenAid, and Maytag, and Whirlpool. They're all pretty much the same machine internal, and they just put their name on it so they could sell the same machine 5 different times. I don't know why they do that, but heck, if it sells more, then it's better. How your ice maker works, just basically, if we look at this image right here, this is what we call the evaporator, and it runs at about the same temperature and pressure a regular refrigerator would run. So if you're using R134A, you're going to probably have a 0 psi evaporator running about 15 degrees below zero. And I'll go in a little bit more detail, but water circulated over this evaporator, and then the excess runs off into a trough that returns. Once the ice reaches what they call the desired thickness, which I've been reading instructions on this. I don't know how they can actually control the thickness, and I'll explain to you what I see different in this unit. And I do have to get a confirmation from Whirlpool on that, so I don't want to say this is exactly how it works, but I read this entire manual back to forth, so we'll go over what some of the important parts of it. So once the ice is reached, the unit does what they call a bypass. A valve opens up and lets the refrigerant from the condenser go straight to the evaporator, which warms it up. The ice sheet slides down into this metal cutting grid, and the cutting grid gets warm and cuts the ice. Now, this cutting grid is low voltage and not very hot, because if it was, it would melt the cubes before they even reach the bin. So that's just a basic operation where water circulates over the evaporator, it cycles that slab, and then cuts it into pieces. So let's take a little bit more closer look at some of the components, point out some things, location of components, and how it works. Um, in this refrigeration system, we're using R134A. I have not seen, and I didn't check if my new ones that we just got is R600 yet. Here you got your compressor, your condenser. This is what we call the hot gas valve. If you're not familiar with how these ice makers work, um, the refrigeration system is just like a refrigerator. It has a condenser and evaporator, but it doesn't have a defrost system like a refrigerator. It uses high pressure refrigerant straight from the discharge line. Normally this would go here into your condenser, but when it wants to drop the ice, this hot gas valve opens up, and that freon doesn't go to the condenser. It goes straight from the compressor to the evaporator, and that's how the ice slides off the unit. One of the things that they've added, which I haven't seen, I haven't looked at the new one that we got, I haven't even opened it up yet, is they've added something called a condenser accumulator tube. Now, I think the ones we have, that might be called the accumulator tube, and what its purpose is to trap liquid refrigerant. I have here a drawing of an accumulator, and when we have a system running normally, it pumps high pressure refrigerant into the condenser. It converts that vapor into liquid refrigerant, and that goes through a capillary tube to the evaporator, and the heat of the evaporator is supposed to turn that liquid back to a vapor. That's the normal cycle. But if you're bypassing the condenser and you're going over the evaporator to release the heat, it is possible some of the refrigerant in liquid form can get back to your compressor and damage your compressor. So accumulator, here's what an accumulator looks like. And this is one that's cut open. I did a little bit of a drawing to sort of explain. So what happens is they pump into the accumulator, and refrigerant is forced to the bottom of the accumulator. So refrigerant that's in liquid form is too heavy to go back out of our accumulator, so it'll be trapped at the bottom. But this is going back to our suction line of our compressor. So that suction line is going to take all this vapor and pull it back into the compressor, and that'll lower the pressure on our accumulator, causing the remaining liquid refrigerant to boil off as a vapor, so that we sort of like prevent it from going into the compressor as a liquid with an accumulator. That's the main purpose of that. So if we look here in ice production, this is, we're going to go through like how refrigerant flows through the system first. So the compressor pumps out through here what we call the discharge line. This is where the condenser accumulating tube is. I think that's just this big fat tube that you'll see right in front of the condenser when you open up the front of the unit. And you'll see a pipe going to the condenser or going to the hot gas valve. So if you are cooling and creating ice, the refrigerant's going to flow here into the condenser first. This valve will be closed, so the Freon can't go that way. Go through our condenser this way, through the filter, and up through our capillary tube into the evaporator here. And as water flows over it, it freezes, and then it comes back down through our suction line right here. Notice we have another accumulator on our evaporator, because as we're producing ice, the water that's flowing over the evaporator is providing heat to cause the refrigerant to vaporize. So as the ice starts to build up, there's less heat on the evaporator. So again, we're using an accumulator here to prevent liquid refrigerant coming back during the cooling cycle. The condenser accumulator is to prevent liquid refrigerant from coming back during the ice ejection cycle. So this water is constantly flowing over the evaporator and circulating until it builds up ice. And I'm going to get a little more detail as we go through the manual as far as how that works, because the cycle of the older ones versus the newer ones, initiating that cycle is now been done a little differently. So in the harvest mode, this is where we're going to have some changes. There is a water level sensor in the reservoir that the machine fills up to circulate over the unit. And I'll show you pictures of that as we go through. The older ice makers, the original design that they made, didn't have anything that controlled the water inside the recirculation container there. It would just fill up, and anything over the amount would run in through an overflow and just run right out the drain. But they would just run it for a certain amount of time to fill up with water. Now they have a like a float switch, or actually it's not a float switch. It's a unit that's in the water, and it runs a low voltage current through the water. And once the water reaches a certain level, the board knows how much water is in there. So the cycle of the ice maker is done actually by the water level control. So if we look here, below the water level signals electronic control to terminate the power to the condenser fan. So once the water level gets to a certain level, there's a thermistor that if the temperature's over 115 degrees, the condenser fan's going to run. If it's lower, then they're not going to turn on, especially if someone has it in a garage or a basement where there's colder weather. And the reservoir drain pump is activated to drain the reservoir. So every time we go through an ice ejection cycle, they want to make sure that we have the freshest water, the cleanest machine inside. So they try to get rid of that water and put fresh water in there. The old design would just fill up till it overflowed, and hopefully it overflowed enough that we'd have fresh water. This particular unit, they added a separate drain valve. The older ones didn't have a drain valve, and it would pump out the water during the ice ejection cycle and then fill up with fresh water. And by doing that, that helped assure that all the old water that was inside that machine is removed. And one of the reasons why they did it is if you heat water or refrigerate water, it tends to separate hard water deposits, calcium, lime, and iron, and other deposits and minerals that it's in the water will separate from the water as the water freezes. And they're saying as the water flows over that slab of ice, it flushes those minerals back into your reservoir. Well, if we're not completely draining that reservoir out over a period of time, depending on whether the customer has really good water or well water in a poor, filtered environment, calcium and lime can build up all over the internal components of that machine. So the older machine didn't drain that water out, so that reservoir over time would actually build up with more hard water deposits, and the only way to get that out is you'd have to manually drain it. On the older ones, you had a little cap you could unscrew and run that water right out of the unit, and it would fill up with fresh water that way. So basically, I'm not going to read this to you, but if the water level sensor is disconnected or open, the control defaults to 25 minutes. So let's just say that the unit is running. The water level sensor does two functions. One, it tells the machine how much water came in as a fill. The other thing is instead of using a thermistor sensor that tells the machine to drop the ice, it uses the water level sensor. So it fills up with a certain amount of water. The water level sensor tells the machine, okay, the reservoir is full. As it makes ice, the water in that reservoir is going to freeze into ice, so the container is going to gradually lose the liquid water as it freezes. Well, they use the water level sensor. If the water gets down to a certain level, it's assumed, okay, well, now that all that water is gone, it's got to be ice up in the slab. Let's go ahead and drop the ice. So instead of using a thermistor on the suction line, they're using a water level sensor, and I'll point them out to you as we go through the slides. So this is one of the main changes that they did on the newer unit. They've added a drain valve. They've added a water level sensor to the system and changed the way it's cycled. Now, if the water level sensor did not tell the machine it was working properly, then it would default to working like the older machine where it would overflow the water, and after about 25 minutes of cycle operation, it will automatically go into an ice ejection or harvest mode like the older units did. So this works off of the water level sensor, and if not, the board is supposed to take over as far as a time frame. So let's take a look at the ice making process. Here you can see the pictures of the water in the slab that I showed you in the beginning. Here we opened it up, and I'm going to zoom in on that in a second. This is the, let me get my mouse pointer here. So if we look here, you know what, I'm going to have to open up the actual PDF, because if I zoom in on that, that's going to be a blurry picture. So if we look here, what they did is they've removed the front access panel, they've removed the water filter. This is another new a new item that's been added, is that they have water filters inside the ice maker. One second, I lost my screen here. I'm trying to find you guys. I don't even see my Google Meet screen. You all are still there, right?
We're here.
Okay, for some reason I cannot see my screen. There you are. Okay, I got it now. I'm sorry. Okay, so here's the cutter grid. This cutter grid is low voltage, and we'll talk about that when we get on the schematics. And this is the evaporator. Now notice these lines on the evaporator. Those lines are the actual refrigerant tubing lines underneath, and they electrically weld it, like arc weld it, to the underside of the stainless steel plate. I've run into a few of these ice makers right here where my mouse pointer is pointing here or here where they arc weld them. I have seen that they got enough rust on that plate that it's actually had a refrigerant leak. And it's sort of bad when that happens, because if we lose Freon, not only does Freon go out, we lose cooling, but this is the low voltage side, and running on 134, it's going to pull into a vacuum and possibly suck moisture into your evaporator and get water into your refrigerant system. Now, up here, this white tube is the recirculation hose going to a diffuser here, which has a bunch of little holes on it, and that's what pours the water onto this evaporator plate. And when it runs down to the end of the plate right here, it drips back down into this container you can see down below. And this black box here is your drain pump, but behind this white cover on top of it is your recirculation pump. So we have two pumps on the newer units, where the older ones only had a recirculation pump. So again, the cutter grid is here. This is our evaporator plate, and this is where our water is circulating over our unit. Let me zoom back out. The evaporator plate, if you could see right there, and I'll zoom back into that picture. I don't know if it was in the other picture. You'll see a little quick disconnect plug. You can't see where it plugs into. The gentleman that's lifting it up, there's a plug right there. So this plugs right into the control board, which is above the cutter grid. And there's another plug here, and you can see a wire hanging down here. This is your bin level sensor. This is what tells the ice maker, hey, we've made enough ice, don't make any more, otherwise the customer is going to open up the door and it's going to fall out. So this is the unit or the sensor that tells the unit that the bucket is full and stop producing ice. Once the ice drops below this line right here, it's going to start making ice again. That plug is located right here above that arrow, and I'll see if I zoom in just a little more. And there's a plug right here, which is the plug for the bin level sensor. Now there is an evaporator thermistor on this unit. I might be plugged in behind this wire harness here. I cannot see it, but there is one other connector that's inside of this unit. So we have, in order to get into the computer controls, you have to lift up the top like this, and you'll have to disconnect the three plugs. One where the guy's hand is, that goes to the cutter grid here. This is the wire to the bin level sensor, and there should be a third wire, which I don't see, which plugs into the board. It's our evaporator thermistor. Now these wires here are not insulated wires. That means the electrical current running through those wires are running through bare metal wires. If you touch them, you might feel a small tingle or shock because of the low voltage, but it's not going to bite like 120 volts or 240 volts would. They do sell the wires as an individual kit, but I'm going to be honest with you. You have to run the wire and pull the wire taut and straight, and there's a screw right here that the wire attaches to, and there's more on the other side. It's very hard to rewire one of these. You are better off buying the whole cutter grid as a complete assembly and not try to rewire it. It's not easy to get it to the right specs. So here's a picture of someone taking the cutter grid out. It's just usually 2 screws in the front on either side here, right underneath, that hold it in place. And 1 quick disconnect, which I showed you. You can see it here in this picture a little bit better. That is the plug into the board that cutter grid plugs into right there. The other picture, the guy's hand was blocking that view. So going to here is a breakdown of all the components. Let's identify the components on the board. Making some of these changes again is to ensure that we have clean, fresh water. Even though that this is in a cold environment, it is not like your refrigerator. It will build up mold and algae in your reservoir, and in the back behind this cover, you'll also find that buildup. I highly recommend, if you ever get a service call, is to, one, they do have a cleaning solution that can be put in the bin and recirculated so the internal components are clean. But you can remove this reservoir here with just these 2 wing nuts, and you can manually clean them out. So I would always recommend selling them a repair, but then offering them at a discounted rate if they'd like you to clean it out. You can sell them the solution, and you can also sell them the service on top of this repair to clean it. These units go for about $1,500 to $1,700. So you could make $500 to $700 between a repair and selling the cleaning on the job. So let's start from the bottom and identify the components and show you how some of these things operate. This is your water valve. This is located down in the bottom left hand on the outside of the compartment next to the condenser. And then there's a hose that runs up and it comes in right here. You see this hose running at an angle, and this water is supposed to go into this reservoir. Now this little hole right here is an overflow. So if the water valve is turned on for an extended period of time, that water will run down through that hole, run down this hose here, and in the bucket that your ice is stored, there's a drain hole in the back. And so that water will just run right out the drain. Here is a cap that I said you can manually drain the water out. So if you're going to remove this compartment for service, just pull the cap off, let the water run out, and then these 2 screws, you can pull it right out. Here we have the drain pump mounted on the bottom, and that drain pump is going to just drain out this reservoir right here. That's all that drain pump does, is to empty out our reservoir. Our recirculation pump, like I said, is right on top of it, and I got some other pictures I can show you a little bit better. Those 2 are there. The drain pump can be removed without taking the whole thing apart. If you're going to do any service to this area, you're going to have to remove the cutter grid like they're showing you in this picture here. So if you have to do the circulation pump, you have to remove the reservoir. I think you can remove this pump motor just by twisting it and pulling it out and just quickly unplugging it. The only thing is all the wiring's up here, so this pump's got a wire running behind the reservoir and coming up to behind the evaporator. So on top of the recirculation pump was our water level sensor. That's located in this area here, and I'll show you a better picture of that as well. And that's the unit now that's also a new component besides the drain pump. That is what's telling the board if you have enough water in there. One of the biggest problems we have with these ice machines is that over a period of time they run out of water in the circulation pump, and you'll hear the pump go is where it's sucking air and it's not circulating air over the evaporator. On the older ones, it was just usually either low water pressure to the customer's home or a bad water valve. So if you're running into a customer saying poor or slow or no ice production, and you're hearing that circulation pump laboring or sucking air, most likely it's your water valve problem here. So we have the evaporator. This is the water distribution tube, and the water comes out of little holes onto the evaporator and runs down. This little guard here is between the evaporator and the cutting grid, and that water falls down in here and it guides it back into our recirculation pump there. Now the components in the back of the unit. I'm going to switch back and forth between this and the actual manual. In the back of the unit, we got our compressor access. If you look here, you can see a 2x4. You can remove the screws on the side of the cabinet and actually lift it up to service the compressor and replace the compressor. If you had to change the evaporator, you could take the entire cover off. That these lines run here and are covered by a panel. You can see two screws right there. See if I can zoom in a little bit on my manual to show you. I think it is this one here. Let me see if I can go to the components on the back. That's not the back. Okay, here's that picture. So on the back of this unit, you can see two screws, and it's hard probably to tell, but there's a panel here that's bent. This panel is hiding the water fill tube and your refrigerant lines that are running from your compressor to your evaporator. If you had to change your evaporator, you have to remove this rear cover so you can get to those lines. So here's our dryer filter and our cap tube, suction line, regular components, condenser, fan. Here you can see the hot gas valve. You'll be able to see that from the front or back. This is the valve again that lets the refrigerant bypass the condenser and run straight to the evaporator for ice removal. Now you notice it says without condensate pump. This is called a condensate pump, and on the last page I have a picture of the kit. That condensate pump is if the customer doesn't have sufficient water drainage. And I'll explain here. If you look at this hose here, this yellowish looking hose, that's the drain hose, and the way these units are designed is that you're supposed to have a floor drain or a hole in the floor, or you could actually run this to another hose and run it out the back wall if the customer has the ability, like in a garage, to drill a hole through a wall and just run it into the yard out back. That this drain is a gravity-fed drain pump, but if the customer is, let's say that they live in a condo on the beach and they're on the 20th floor, they don't have a floor drain in their apartment, you can add a condensate pump. It's similar to what they use in an air conditioning system. It plugs into the ice machine, and it comes with a different drain hose. You remove the factory hose and you put it here so it runs into here, and there's a float inside, and once the float reaches a certain level, this hose here runs to either your washing machine drain, or you plumb it into your underneath your sink and run it into your kitchen sink depending on where you install it, or you could even run it up and through the house and 10-20 feet away, and it'll drain the water. Notice this ice maker plug. Now the older ones right here, and I can't really draw on this one. Let me see if I can screen capture this and bring it to the other screen so I can draw on it. This is important because if there's a problem with this, it will not produce ice. So you have to be aware of it. I'm going to just paste it right here and just overwrite, just over the top of everything else. So older ones, they used to have a plug right here. And if you look at them, that this plug right here has a cap in it that has some bypass pins. So on this plug here, if it's missing the cap that goes on it, and it's like almost like a rubbery gel cap, not it, almost the same material as this hose here. And if this cap's not plugged in, the ice maker won't run. Why? Because the older ice condensate pumps would plug right into the bottom of the ice maker, and if it was plugged into the bottom of the ice maker and you removed that bypass there, what would happen is there is a safety switch here. If your condensate pump fails to pump out, let's just say the condensate pump build up algae, pump's running but the water's not going out. Well, the next thing is that pump's going to overflow with water and it's going to be all over the place. So they put a safety float switch in there that will shut the ice maker off and not allow the ice maker to run until this is emptied out. So the newer one now, they put a regular 120 volt outlet in the actual pump, and this plug that you're actually looking at is the regular ice maker plug running over here feeding the ice maker. So the ice maker plugs into your condensate pump, then your condensate pump will plug into the wall. So it still has a safety switch built in that if your condensate pump is full and is not draining, your ice maker will not run. So before you tear your whole ice machine apart, you want to check your condensate pump and make sure that it's not full and overflowing and leaking in the customer's home. So central air conditioners use the same type of system. If you put an AC in an older home and it don't have a place to drain the water out, they use the same type of system here, a pump, that the water that the AC drips into that pump, and then a float switch will tell it to pump out, and it has a safety switch in that pump too, that if it fills up, it'll shut the customer's home AC off. Now remember, if you guys have any questions, don't hesitate to say, excuse me, I got a question. So here is the pump pulled out, and I'm going to show you the kit at the end of this presentation. I have the kit and all the parts in it. This here is something new that they've added. They've added an inductor and a thermistor underneath the unit. I'm going to go back to my manual so I can zoom in on that for you. Let me see here. My manual is this one. It's a little hard to tell. So if you look here, it's strapped down right here. It has two items in it. It is an inductor and a thermistor. The purpose of the thermistor is to measure the temperature of the condensing unit to make sure that we're not overheating the condenser. A lot of people don't service these like the refrigerators. The coils need to be cleaned, at least once a year to make sure this thing's going to run efficiently. But if it runs too hot, that thermistor will sense the temperature, and it says here, if the temperature of the machine compartment, and when we're saying machine compartment, we're talking about the compressor condenser area, exceeds 115 degrees, then during the next cycle, the condenser fan remains on to cool the area down. 5 volts DC is supplied to the thermistor. Now the thermistor is what tells it what the temperature is, and the other component in there is called an inductor. All that is basically a way to control the voltage going to condenser fan. I did not look at this. Well, I'll look at the schematic with you. I think it's a variable speed condenser fan motor, and to help control the voltage going to that motor, they just added an inductor coil. I've never really seen many of them added, so they might have had a problem with voltage spikes coming from the board or something, that they went ahead and added this in just in case. I don't think it's a mandatory thing that has to be in there, but if it failed, your condenser fan would not run, and I'll show you that in the schematic. So this unit has a diagnostic mode. The older ones also have a diagnostic mode. By pressing these two buttons on the left here, the on button and the clean button, and holding them, you have to unplug the machine or power the machine off, and as soon as you power it on, you have to press these two within 20 seconds of powering the unit back up. So if the unit's been running, I don't think it will go into a diagnostic mode. You'll have to turn it off and turn it back on. So when you get into the diagnostic mode, make sure you press the clean on both at the same time. Press and hold the clean button and then hold the on button. So don't press them both simultaneously. Put your finger on the clean, and while you're pressing down on the clean, then press down on your on button. So in other words, most of the times when you go to diagnostic, you try to press both buttons at the same time. You're going to press and hold the clean and then press and hold the on button, both of them at the same time, and that'll get you into the diagnostics. Once you're in diagnostics, all the LEDs will begin to flash. So if you see this, all these LEDs flash. The reason why they do that, one, is to tell you you're in diagnostic. Two, in case any of the LEDs on the board are not working, this is a test to light them all up. If you see one that's not working, then your user interface might be defective that has these lights on it. So when we go into a diagnostic mode, this is the chart. Now, it has steps. It has an automatic and a manual mode. If you go into it, I think it just runs through the diagnostics on its own, but you're really not going to use diagnostics like every single step when you go into any machine when you're troubleshooting. You're only going to go into diagnostics of problems that you're having with that machine. If it's not filling, then I'm going to go over to the ice or the water fill valve right here, step number 5. If I had something with the ice thickness and I wanted to see what the setting of the ice thickness was, 2 blinks tell me that it's thin, 4 blinks normal, 6 blinks thick, and that up here at the very top is telling you the max ice. So when you look here, one of these lights is going to say max ice. It might be underneath where his finger says, I don't know, it says fast ice. That might be what they're calling max ice. So that LED would be on. The clean LED is off, and this is off when we're checking the ice thickness. So you have to see what lights are on and what lights are off to know what step you are in. Now, if you think that the evaporator thermistor or the bin thermistor is bad, it's just as easy to go into diagnostic and test those thermistors right from the user interface than having to take it apart and put an ohm meter on those components. So this diagnostic is good, but remember, you don't need to go through every step to test the ice machine out. Just find what your problem is with the ice machine and go into that step and test that. So here is the schematic and a breakdown of the parts. The unit has an external transformer. This is called a step-down transformer, and that is located right here. Let me get my marker. That's located right here. It's got line 1, which is black, coming in, and this is neutral, which runs into the board here. And this should have 120 volts all of the time. Okay? We have 2 outputs, the blue wires and the red wires. The blue wires are the higher voltage for the cutting grid. That's usually, did they have the voltage on that one picture? Let me see. I think it did say the voltage on the grid. The heater grid operates on 9.4 volts and is about 5 ohms. So the output of that transformer here on the cutting grid assembly is 4 I think it said, or 9.6. So some of the older ones, I think it was 12 volts. Now this voltage here is voltage that is going to the board, but look how the circulation pump and the drain pump run back to this output here. So that voltage coming off of the board here goes into the gray here, and then there's some relays that's sending that voltage out to your pumps. Since your pumps are not connected to line 1 and neutral, those two pumps are not 120 volt pumps. Those are low voltage pumps. And I think they said that in the book here that they run off of 5 volts is to the thermistor. I don't remember what they said the voltage was of the circulation pumps. Just see if I can find that. They didn't post it here. I'll have to find that in the manual. I don't know the exact voltage that pump runs off of, but it's not the 9 volts. It's probably running off a little bit more volts. Now, all the rest of the components that have neutral connected to them, the water valve, the hot gas, the condenser fan, the compressor, all of them are 120 volts if they connect to neutral. The thermistors are 5 volts. And all of these sensors and user interface are low voltage as well. Here it says the LED is 14 volts DC. So this might be a 14 volt output right here. And that's what's feeding the water level sensor, the module, and your 2 pumps. Okay, here, if it's a unit that uses a filter, if there's no filter in there, it might not let the machine operate. Some of these newer units now, I know GE now has changed their filters and they put a chip in their water filters. And if that water filter gets a certain amount of usage, the refrigerator won't let the ice and water work until they change the filter. And if a customer buys an aftermarket water filter, it will not work with the refrigerator. They'll get no ice and water, because the new aftermarket filter does not have the chip. That's how GE's trying to make sure that they get to sell more filters. It doesn't make it work any better. So that's the board and the voltages on the board. If you look inside this picture, we also have some components. This is our user interface board right here. This is the back side of it where you're pressing the 2 buttons to go into the clean mode. This is the step down transformer. It's not part of the main control board and is ordered separately. Here is our main control board, and then the filter switch is built into the filter housing assembly. It's underneath here. It looks like a light bulb switch on a refrigerator. And right here is a reed switch. This is used when the customer opens and closes the door. A magnet on the door closes that switch so it turns the light on and off. You got a question? No?
No, I was just you mentioned something about the voltage to the pumps.
Yes.
It's page 4-5 on the left hand side there. They mentioned the for the drain and recirc as well as the reservoir drain pumps.
And so they're running on, you said 4-5?
Yeah, 4-5, just under electrical system. It's I think that's what you were referring to.
Yes. Okay, so the transformer changes 120 to 9.4 and 14. So I was right. The 14 volts is what's coming out of the other secondary, that transformer. 12 volts AC for the drain and recirculation pump. So I guess we're getting 14 off of the transformer, and then the control board's going to drop the voltage to 12 by using some resistors or something. And those pumps are actually running off of 12 and not 14. I assumed it was 14. So you got to be careful not to take those pumps and try to put a 110 volt test cord on there or something to check that unit out. But thank you. So these are all the components that are up inside of it. There is one quick disconnect here. So when you want to service this, you can unplug it and pull this whole assembly out to look at it. If we look here, I'm not going to go through the whole thing, but this is all of our tests and how much voltage should be going to every component. So you always have to check voltage. If you notice, all of these components up here are AC voltage, whether it's 120, 12, or 14. But notice we have some DC voltage components as well, 5 volts, 14 volts. Make sure you refer to this page here, so when you're testing and you're saying, oh, it's 12 volts, let me put it on 12 volts AC, and you're actually trying to check a DC circuit. How you use this to test the components is the P's and J's are the actual whole connector that the wires are connected to the board with. The -1 or -4 is, if we look at this connector, and let me zoom in on it just a little bit, just so people know when they're testing from the board, what does that mean and how to test from the board. So if we look at it, and let's just say, let me pick a component out. So let's go to neutral transformer, 120 hot gas valve. So this neutral for the transformer can be used for the transformer as well as the hot gas valve. They're both 120 volts. So I could use plug 3 pin 1, plug 3 pin 3. So what that means is I find plug 3 here, and notice they are giving you a number 1 here. There's usually a red dot or number 1 printed on the board, but they might have covered them up. This number 1's on the opposite side. So what that little number 1 means is that this first wire's pin 1. There's no wire on pin 2. Here's pin 3. So they want you to check P3-1 and P3-3. P3 means plug number 3, 1, and 3. So you're going to put your meter lead on this one and this one for 120 volts. And what are you testing there? We're testing these two here, which is a white and tan and a violet wire. So this is a white with a tan, and this is our violet wire here. And this is our neutral and our hot gas valve. So this is what sends power to harvest the ice, for example. So that's what this chart is telling you, is where you can put your meter on the board to make voltage tests for troubleshooting. Any questions on the testing of components? Okay, here's where one of the changes has come into play. The older units and the newer units both have an evaporator thermistor. The evaporator thermistor is always on the suction line going back to the compressor. It's sensing the temperature of the refrigerant, and like I said, as ice builds up, we don't pull as much heat. So on the older units, it knows how thick the ice is based on the temperature of the suction line. So if you got water flowing over the evaporator and the ice is 1 inch thick and it's not dropping, the evaporator thermistor on the older ones is what tells the ice maker to drop ice. The newer ones, it's the water level sensor that tells the ice maker to drop ice. So you have to know if you're doing the newer or the older model. And I guess the only way to know is if it has a water level sensor, that's what controls it. And you're going to have to find that on the diagram. So on the older ones, this thermistor went bad a lot, and we had poor ice, or sometimes you would get improper ice thickness because the sensor's not functioning properly. Here is our bin level sensor. This sensor is mounted on the side wall on the right hand side. One screw and one quick disconnect. All you have to do to get it out, you don't have to remove anything else. And the ice, as it fills up into the bucket, will reach this sensor, and then the ice maker will stop producing ice. Now, one thing about these ice makers is a lot of people think when it makes ice, that ice will sit there forever. In a way, ice will be there forever, but it is not like your refrigerator at your home where your ice maker makes ice and it puts it in the bucket and that ice stays in that bucket forever. That is inside of a freezer. The ice machines, they are not that temperature. The ice machines are just a storage unit. Even like commercial machines, when you go to a hotel, for example, the storage bin for all that ice is constantly melting the ice. We call it wet ice. And the reason why they do it is if the ice doesn't get used up, the ice gets stale. It gets taste, it gets odors, and will build up algae. So commercial machines, as well as most residential ice machines, are constantly melting the ice on the bottom and running out the drain and producing fresh ice. It will retain ice for a while, but it's more like a cooler. When you go to the beach and you fill up your cooler, it's going to hold that ice in there until it melts. So this bin level sensor, even though that it tells the machine to stop producing ice, if it's not making ice, it's even warmer because the evaporator is not working, and that ice is going to slowly melt, and then that sensor is going to say, hey, start making ice again. So whenever you want ice or fresh ice, you always take it off the top and don't take it out of the bottom. So here is our recirculation reservoir, and there's a quick disconnect here. We have two connectors here. Actually, there's a third connector. One is for our recirculation pump. The other is for our drain pump, and third is the water level sensor, and I'll show you that in another picture. This compartment here is where the water comes in, and you can see this hose here. It's also here in the picture, and runs the water into this reservoir and fills the unit up. It's very hard to see, but right here is a hole, and that's an overflow hole. So if there's a little bit of remaining water left in it and it goes to fill up and the water level sensor doesn't shut it off, that water will overflow here, run down this hose here, and go out the drain. So that is the overflow. So the top piece here is our recirculation pump, and that recirculation pump runs through this white hose and goes up to our distributor on top of the evaporator, and then it flows back down into here and returns back here. This one on the bottom is our drain pump. So here is our water level sensor. And note what it says here. The water level sensor cannot be checked with an ohm meter or voltmeter. The only way you can tell if this sensor is working correctly or not is you have to go through diagnostics, and step number 10 is the step you need to go into to test that out. So this here are our pump system, but that's the water level sensor. Now here's the drain pump. Okay, so there is a screw here that holds the drain pump in place, and then you just twist and the drain pumps out. One thing that they note is that right here is the impeller that turns around and pumps the water out. And this is the drain hose. Look, it just runs right down here. That's basically where the ice is stored. It doesn't run out the back of the machine. It runs into the bucket where your ice is stored and runs out a gravity-fed drain there. This is the armature that the motor goes over, and that will stay there. You can replace this pump and motor assembly and leave that armature there. Note, when you're probably ordering a drain pump, it might or might not come with this. I haven't looked at the parts breakdown, but if you see this piece sticking up there when you take the motor out, don't think you broke it. That is normal. Here's a picture of here's a transformer for the voltages. So we got 120 volts coming in. That's our black and our white wires here. That's 120 volts coming into the transformer. And we have to have two voltages coming out, 9.4 and 12.8. So it doesn't put out 5. I was incorrect. So the board is what's stepping these voltages down for the sensors, which are like asking for 5 volts or something. This transformer is separate from the main board and can be replaced individually. How would you test it? Well, 120 in, and the 2 red wires would be 12.8 coming out, and the 2 blue wires are going to be 9.4 volts coming out. So that's going to go serve power for our pumps, sensors, and everything else in the unit that does not run off of 120 volts. This is a pump kit, and the recirculation pump, this, if you look, it looks almost like a dishwasher drain hose, because you can drain into your dishwasher drain. But if your dishwasher is already connected to your garbage disposal, you cannot connect this to that same hose, because you will risk having dirty water from your dishwasher feed back through that and get into your pump and possibly contaminate the water inside your system. But if you had a double sink, like a double sink in your home, and your garbage disposal is mounted on one side and your dishwasher is connected to that, on the other drain, they sell a pipe where dishwashers can connect to the regular pipe underneath the sink for the drain, and you could mount that in your kitchen, and this hose would connect there, and it would be separate from your garbage disposal, so you don't risk contaminating and putting dirty food in there. I'm sorry, dirty water in there. Going back to the control board here, let's go to the diagram first. So we have several different voltages going on. Here's our circulation pump, here's our drain pump, bin thermistor, evap thermistor. The unit thermistor is the one I showed you that's on the bottom by the induction coil. You have the user interface. This is the front with the LED lights that you're pressing to activate. Your water level sensor. Oh, actually, you know what? The LED lights may be separate from your user interface. I have not looked at the parts breakdown, but you may have an LED board, and then your user interface probably plugs into that, which then goes back to the main board. Let me see if I can zoom in on it and take a better look at this. I did not check that out before preparing for this class. I apologize. I don't see, I see where the input voltage can go in there, but I don't see where the user interface is either connected to the main board or to this board. It should be connected to this board. Let me see, orange, tan, and black. This might be this plug right here. No, that's not orange, tan, and black. That looks like red, tan, and black. And this is red and white. It's going to be hard for me to tell. I'm going to open up the one I have at my school and go through and confirm these colors on there as far as the voltages. So, filter switch, again, if the filter's not in there, I don't think the ice maker will work, because water's got to flow through the back of this compartment. If filter's not there, the water's going to run out, so they're going to prevent the machine from running when the filter's out. Any questions on some of these things that I've covered, just so I make sure that you all are following me with the components? Okay, so let's just go through the complete cycle of operation from start to finish. I was looking for one thing. Okay, here, this is what I want to point out. In all ice makers, Whirlpool, and again, I don't know if other manufacturers do this, if you unplug them or you turn them off and you turn them back on again, they will go into a almost like a flush cycle to flush out any water. When you unplug an ice maker for service, it doesn't know that you just unplugged it for 1 minute or is unplugged for 20 days. If a customer turns the power off, let's say a customer is a seasonal customer, like we live here in South Florida. We got customers who live in New York and they come down here in the wintertime for 2 or 3 months and then they go back home and they turn the ice machine off. The water, if it's not drained out and it's wiped down properly, is going to build up with algae or mold. So they run this thing through like a 5-minute rinsing process. The water's just going to continue to run and circulate and go over the unit to clean itself out. So when you first plug something in and you're hearing water run, but you're noticing that it's not producing ice, it's going to run into like a self-clean cycle before that happens. So you have to make sure that you're not in the self-clean cycle. So this is what happens when the ice maker turns on. When you first plug it in, it's going to run it for almost 5 minutes through a flushing, rinsing cycle, and water is going to come in here, and the excess water is going to run down our overflow and out this unit. At the very end, I'm not sure, but I would assume they probably run in the drain pump to try to pump any water out at the bottom reservoir, which also comes out this tube and goes out the drain. So now they're going to go to the ice production cycle. We're going to call for water on the water valve, and they said measured fill water in that valve. It's just a water valve, but the water level sensor here is what's telling the unit how much water's in there, so that's why it's called a measured fill water valve. And it'll fill our reservoir up. Once the reservoir fills, it'll shut the valve off and turn on our recirculation pump and our compressor and our condenser fan. Water starts circulating over the top of the evaporator, and because this evaporator is running 15 degrees below zero like a refrigerator, the water is going to start to stick to it as it freezes. And as water slowly flowing over it, the water itself is going to get cold and go back into our reservoir. So we're cooling down our reservoir and making it easier for the ice to produce. It should take anywhere from 20 to 30 minutes to produce one batch of ice. And if you counted how many cubes that would be, you can multiply that by 20 minutes, and it would tell you how long it would take to make about 50 pounds of ice. It's usually within 24 hours that if someone does not take any ice out of the ice bin when it produces ice, it will fill that ice bin up. So it takes about 24 hours to completely refill that unit. Once it starts flowing over, the ice starts building up on the evaporator and starts to get thicker and thicker, and we're going to start running out of water in our reservoir as it turns to ice up here, and that's when our water level sensor says, hey, the ice should be thick enough, let's go ahead and drop that ice. At that point, we initiate the harvest cycle. Now what happens in the harvest cycle is we energize the hot gas valve, which is back here, compressors continuing to run, and that runs hot refrigerant over the evaporator and pumps that high pressure refrigerant here so the slab of ice will just slide off. At the same time it is doing that to remove the ice, we are also sending voltage to our water valve. Our water valve is calling for water and filling up our reservoir. So our drain pump drains out, and this, I think the drain pump initiates on the ice ejection cycle to get any remaining water out. Then the water valve will come on, and then the water level sensor will tell it to stop filling with water. Once the water level sensor has reached its mark, it'll stop filling. That does not tell the machine to start producing ice yet, because it's going to work either by the evaporator thermistor or the time limit. The evaporator thermistor is going to tell the unit, I think they said it was 54 degrees. Let me see if I can find that. The start of the harvest begins when the water level is below the sensor, or max time of 25 minutes. I was trying to find, I think I saw somewhere it said 54 degrees. So once that sensor notices that there's 54 degrees on that suction line, it's going to stop the ice harvest cycle and then reinitiate the ice production. So ice removal is hot gas valve, compressor, and that's it. It just blows hot refrigerant into the evaporator and slides off. Ice production is compressor, condenser fan, recirculation pump. During ice ejection, we have a drain valve and the water valve that are both initiated but not at the same time. So that is the operation. How do we troubleshoot this unit besides the diagnostics? We said that we had a water valve problem. On the old ones, the evap thermistor initiates ice, but on the new ones, the water level sensor initiates ice sensing, or ice harvest. I'm sorry, I misspoke. So if you notice that there's no water in the reservoir, let's just say the water valve went bad, and there's ice stuck on the evaporator, it is possible the water level sensor is not telling the board that, hey, enough water's come out, let's go ahead and fill up with more water. So that is in the ice harvest cycle. So how do we test the components from the board? Let's just do a couple of quick tests through diagnostics. I want to check my evaporator thermistor. Now I can ohm it out, but what if it ohms good, but the board is telling me it's bad? What could happen? Anybody have any idea? No? Okay, well, we want to make sure that we're getting our output voltage on the board. In order to test that, we can look at the board here, and we can see the evaporator thermistor goes to plug P5, pin 3 and 4. I think that was here. Pin 5, pin 3 and 4. That's these two tan wires right here. I can make two different tests from the board for this. One, I can check the voltage and see if I have the 5 volts coming off the board. And two, I can unplug this and put my meter lead on these two wires, and putting them on the two wires, I can ohm out the resistance of my thermistor. Now, the evaporator thermistor is plugged in underneath the unit. It might be easier to get to just the plug of the evaporator and bin thermistor directly to check that out. But in order to check voltages, you have to go to the main board. You will not be able to unplug the thermistor and then make that voltage test to see if it's supplying voltage. Because if you unplug the thermistor, in this case, the board would not see it and then initiate an error or fault, and probably stop the ice maker from working if the thermistor is not evident in the unit. We're coming up on the hour. We went a little bit over. Does anybody have any questions? Yes, Mel.
Yeah, I have one. So just what you were saying about the if the thermistor was unplugged or faulty. I read in this I think it's on page 4-6. I was trying to understand. So if the what was it? Thermistor. Sorry. If the evaporator thermistor is unplugged, the evaporator defaults to a time 4-minute harvest. So, are you saying it? Could this ice maker still function as designed even without the thermistor, or no? Because that says that it would still default.
Yeah,
Um,
yes, but the older ones will not, only
oh,
because they use the evaporator thermistor to know how thick the ice is and when to harvest. So on the older ones, definitely it's not going to function properly or function at all if the thermistor is disconnected. On this one here, if you disconnect it and it can't see it, it's just going to override it and then cause the ice to drop at 25 minutes intervals. But does that mean the ice thickness might not be right? The customer might call you out and say, "Hey, listen, my ice thickness may not be right." How would we approach that? You have to know the operation. So normally, what causes it to drop ice? The water level sensor, right? But what
right.
if I have a water valve problem or a water pressure problem? Will the ice maker fill up with enough water? Maybe not. Maybe
Yeah.
maybe it fills halfway instead of all the way. So then when it's producing ice, once that water's emptied, the water sensor is going to say, well, you know, the ice should be the right thickness because there's no more water left, and drop that ice, but the ice thickness may not be right. So here you are going to service something with an ice thickness problem. They're telling you, oh, my ice is too thin. And you say, well, maybe the water level sensor is bad because it's telling it to drop too soon, but you could also have a fill problem. They do tell you somewhere in here the amount of water approximately it fills with. Let me see. Control F. Here. So thin ice uses 35 ounces, normal ice uses 38, and thick uses about 41 ounces. So what I would do is I would drain your bucket. Remember I showed that little cap in the picture. I would manually drain that water out of the bucket, and then I would initiate a cycle through diagnostics, and then I would put a cup underneath that drain cap and then drain it out again, and measure how much water I'm actually getting to see if it's filling up with the right amount of water. If it's filling up with the right amount of water and we're not getting the thickness, then we're having a problem. If it's not filling up with the right amount of water and we're not getting the thickness, then we have a fill problem. So here's where the water level is, and I think, let me see if I can show it. That little cap right here, where it says manual drain, I can zoom in on it. You can unscrew that cap, and this is where the ice is stored. You can get right there underneath there, and you can drain that water into a cap and measure the amount of water that is in this reservoir to see if it's filling up right. So you know if you have a water fill problem or a water level sensor problem. Does that make sense?
Yes, it does.
Anybody got any other questions about anything with this ice machine? All right, so I guess one day next week, if I can find some time in the class, is I'll take I got a brand new one of the machines that just bought it this year. It hasn't even been hooked up yet, and we'll take it apart and identify the components, and we'll do some manual tests, and I'll post that up on the YouTube channel. We'll go through each component. This is how you test it. This is how you remove it, and I'll make a video of actually servicing it now that we made a video on what the components are, the schematics, and breaking down its function. So that will add a little bit more to this. So if we don't have any other questions, I guess we'll end it for today, and I'll post this up later today on the member section of, well, I'll just put it on the public section of our YouTube channel. But other than that, yeah, if you don't have any questions, one last chance. Jonas, I see you snuck in, didn't say hi.
Yes, Rick, I'm sorry. I didn't want to interrupt.
It's okay.
I made it late. I'm sorry, though.
It's all right. I recorded it. I'll post it up online today so you can watch it. And then, like I said, I do plan on making a follow-up video. And I was supposed to make it this week too. I did not get a chance. I was substituting for the air conditioning instructor in my school during the daytime and teaching my class full-time at night. And I tell you, I was really dragging. 2 weeks of that was really killing me. But someone asked me a question about different brazing rods and which ones do we use for what types of brazing. You know, why would you use 15 over 45 or something like that? So I'm going to try to make another video on that this week as well and go over the different brazes and also demonstrate them. And I'm also going to do aluminum brazing, like if you're going to braze an evaporator, and show you some of the struggles we had in class and what I found finally worked. And I'll demonstrate brazing aluminum tubing together, so if you had to repair an evaporator or something, you can do that. So if you have any questions, feel free to email me or reach out to me, and I'll be more than happy to answer them for you. Other than that, y'all have a great weekend.
Thank you for everything, Rick. Have a good weekend as well. Thanks so much.
You too. Bye-bye.
Bye.